This is the summary for Chapter 8, Part 2. This part was devoted to the theory behind applicative functors and profunctors. To motivate that theory, I asked the question of how we can derive all those functions map2, map3, map4, and so on in a systematic way, or even to avoid having them in the code but replace them with a flexible construction, which was possible using the function called app. In this way I motivated that function. I illustrate how fmap 2, 3, and so on can be represented through app, and also how to describe certain syntax that people use to avoid using these fmap 2, 3, and so on functions altogether. I also show how the zip function is derived from map2, and I show that they are equivalent, just as app was equivalent to map2. I also note the pattern where a natural transformation is equivalent to a lifting, and I comment on the occurrence of this pattern in our proofs. I prove also that app and zip are equivalent. This is an interesting equivalence showing that applicative functors can be defined either using app and pure or using zip and pure equivalently. I then look at what laws the methods must satisfy. The motivation for the applicative laws comes from representing map2 as a replacement for monadic code of this kind. And therefore monadic laws give rise to certain applicative laws. First I derive the naturality laws, and then the associativity and identity laws for map2. I then formulate these laws in a short notation so that it is easier to do calculations with them. I express map through zip and start deriving laws for zip. The naturality law for zip can be formulated as an equation like this, and the associativity law for zip requires some isomorphisms between functor types that have nested tuples like this and like that. I explain what that isomorphism is and how we introduce this equivalence relation or symbol to indicate that we will insert those isomorphisms like this one wherever necessary. I illustrate on this diagram how the associativity law is formulated using types explicitly. Identity law is also derived more easily if we use a method that I call wrapped unit, which is a value of type f of unit, and I show its equivalence to having the pure method. And this significantly simplifies formulations of the identity laws. I show these formulations become like this, where we introduce another implicit isomorphism that we use at any time, which is called phi. Phi is an isomorphism that introduces a unit value into a tuple. Introducing the syntax for the zip as infix function or infix operation, we can rewrite the laws for zip and wrapped unit in this way, which is almost the same as laws of a monoid, with exception that there are some transformations, isomorphisms assumed in this equivalence, and also each of these values has a different type parameter. So they're indexed by the type parameter, so to speak. Naturality law and these laws are the laws of the monoid, the laws of the applicative. the wrapped unit by itself has no laws, and this is the simplest formulation of the laws of the applicative. I show that there is a third naturality law for map2 that follows automatically if we define map2 through zip. We missed that law when we formulated the laws for map2, starting from monad laws intuitively. Zippable functors I define as those that have only the associativity law and naturality laws. Applicative functors are those that have all these laws, together with naturality laws for the zip function. I explained that applicative functors are a strict superset of monadic functors, and that applicative functor implementation may disagree with the monad implementation. I explained what that means. I formulate explicitly the third naturality law for map2 that follows automatically, and I'll show why. Then I also reformulate the app operation in terms of a lifting from this type of functions to this type of functions. And the lifting intuitively should obey two laws, identity and composition laws. And I show that indeed app obeys these laws. These are the laws formulated using the operation, which is the composition using app, which is defined like this. And I show that the first three laws of these are essentially the laws of a category. If we consider this type as the morphism type of the category, and identity morphism is the pure of the identity. So then I show that the category laws follow from the map laws. I also derive the app laws, which are the laws of the lifting, which is that identity when lifted becomes identity, and composition when lifted becomes composition, except that here we need to use this twisted composition, so to speak. In other words, composition in the category rather than simple function composition. Here it is a simple function composition of functions of this type. But for these, this is not a function type, so we cannot just compose it using functions, and that's why this special twisted composition or category composition operation is required. Having analyzed all the laws in depth, I go on to consider constructions that make new applicative functors out of previous ones. I list some of these constructions and derive the laws for all of them. I then give an example of an applicative functor that is a lazy list, and it disagrees in the implementation of zip with the monad implementation of zip. I show why that is necessary and how that works. I then give examples of functors that are not applicative, and I use the Curry-Howard library in order to check that there are no implementations for the zip operation for these functors that satisfy the laws. I then comment on the fact that monoids have all the constructions required to make exponential polynomial types, and all the basic types or the primitive types, and as well as collection types, are also monoids. Therefore, if you make any type expression like this using the product, the sum or disjunction, and the function operations out of primitive types or collections of primitive types or of types like this, all of these are monoids, and the constructions show you how to define the monoid instances, at least in one way. I give an example of a non-monoid type, and this is because it contains type parameters. So if a type does not contain type parameters, in other words, it's non-parameterized, then it's a monoid. Then I use constructions derived previously to show that all polynomial functors with monoidal coefficients are applicative functors. And I give examples of such polynomial functors with monoidal coefficients. I then go on to consider contrafunctors. Contrafunctors are defined as functors, type constructors that have contramap with the contracomposition law. Applicative contrafunctors are defined by using the zip and wrapped unit methods, and this allows us to define applicative contrafunctors in exactly the same way with exactly the same laws as applicative functors. I comment on the differences between applicative functors and contrafunctors, namely they don't have any analog of app, and they also don't have a good analog of pure. I show constructions that build new applicative contrafunctors out of previous ones. I prove that the laws of applicative contrafunctor hold in all of these constructions, and it follows then that all exponential polynomial contrafunctors with monoidal coefficients are automatically applicative, because these constructions cover all the type operations that construct exponential polynomial types. I then generalize from functors and contrafunctors to profunctors, which are type constructors that are neither functors nor contrafunctors because they combine both functor and contrafunctor features. They combine type parameter in contravariant and covariant positions. These are examples of profunctors. This is an example of a non-profunctor. Just to build intuition about what they are, I give a more rigorous definition and show that the laws of profunctor hold automatically if the laws hold for functor and contrafunctor of this type function that is involved in the definition of the profunctor. They don't have map or contramap, they have a method that Scala Z library calls xmap and the cats library calls imap, which is of this type signature. And I comment that all exponential polynomial type constructors are automatically profunctors. I define applicative profunctors by using the zip and wrapped unit methods with exactly the same laws as before. There is no corresponding app operation, but there is a pure operation. I show some constructions that build new applicative profunctors out of previous ones and show that the laws hold for them. I then define commutative applicative functors. This is a property of applicative functors that is similar to the property of commutativity for monoids. You can interchange FA, FB, or FB, FA, and the zip has the same result, up to the type equivalence through the isomorphism that you can just map over the F functor that interchanges the tuple parts in the type. And I comment on what it means when an applicative functor is commutative. I give examples of commutative and non-commutative applicative functors and show why commutative property makes it easier to prove associativity for applicative functors. Finally, I summarize all of the type classes we considered in the previous tutorials and in this one using a categorical picture. I look at the lifting and its type signature, and I show that every time we had a type class with a lifting, we had a law for lifting, which were functor laws, and the law for the function type, which I called the twisted type before, and which in the mathematical language is called a morphism, which is this twisted function type that is defined differently for every category. So for the applicative functors category, it's defined like this, but for other type classes, the twisted type or the morphism function type is defined differently. However, every time, as I show, every time the same category laws hold, the identity and the composition law, and the same functor laws hold for the lifting, namely identity is mapped to identity and composition is mapped to composition. I explained that this picture summarizes and generalizes all the type classes we have considered in a single scheme that starts from a definition of the morphism type, imposes the same fixed set of laws, derives the lifting type, imposes the laws on that, and then derive what are the properties of functors f that satisfy, or contrafunctors or profunctors that satisfy these laws, and then we derive constructions systematically that build new such functors out of old ones. So this is the scheme that summarizes and generalizes all the type classes that we have seen in the same way, which gives us two benefits. Even though, as I explained, we cannot really write any new code that we couldn't write before we have seen this table. But there are two benefits that we derive, which is one, we have assurance that the choice of laws that we made is reasonable and correct, that we haven't missed any laws, and that we haven't added laws that are unnecessary. We have motivated the laws for these type classes from first principles, from intuitions about code. But our intuitions could fail, and this scheme provides a good guarantee that all these laws, as we have chosen them intuitively, are actually coherent, and they are exactly the right set of laws that are necessary. The second benefit we get from this picture is that we can generalize to more type classes, to type classes we haven't yet considered. One such generalization is if we choose the morphism type like this, and this corresponds to the comonad, which is a type class we have not yet considered. Other than this, I comment that there aren't, or doesn't seem to be, other useful generalizations, such as contramonad doesn't seem to exist, and also that contrafunctors that are applicative don't seem to be covered by this picture because they don't have an app lifting, as well as profunctors, they also don't have an app lifting. So not all useful classes are necessarily in this scheme, but nevertheless, this is a very useful conceptual generalization that allows us to go on and to have more assurance about what we're doing. Finally, I show exercises for getting more familiar with the material in this chapter.